Welcome to my channel Engineers Academy. If you people haven't subscribed to my channel yet, kindly subscribe my channel and share with your friends and colleagues. In this video I am going to explain this sample problem, and this sample problem is related to the equilibrium in 3D topic. This is the third sample problem. In this sample problem, it is said that the welded tubular frame is secured to the horizontal XY plane. So this frame is secured to the XY plane. This is the XY plane, right? So this is XY plane, and it is said that it is secured by a ball and socket joint at A. So this is a ball and socket joint at A, right? So this support, this ball and socket joint can support reactions in three directions, in three dimensions, right? That is in X, Y, and Z direction, right? So if we draw those reactions, right? So if I draw those reactions, so this will be one reaction. This will be one reaction that is along X, right? Let's say that this is AX. If I write, so this is AX. Then there will be a reaction along Y. Let's say that this is AY. And similarly, this can support reaction in the Z direction as well, right? So if I draw it, so then let me draw it here, right? So then this will be AZ reaction. Let me put it here, right? So this is AZ. Similarly, this frame is secured at this point B, right? So it is said that and receives supports from the loose fitting ring at B, right? So this is a loose fitting ring. This means that this part of the tubular frame can move both ways, right? In this direction and this direction, right? So this support cannot provide the reaction in the Y direction, right? So hence we will have only reactions in two directions, right? So that is in X and Y. So if I draw those reactions, so one reaction will be in this direction, let's say. So one reaction will be along X. So let me draw it here. So this will be one reaction, let's say, and if I put it here, right, so then at point B, right, so this will be, let's say, BX, and there will be one reaction in the Z direction, right? So there is one reaction like this, and this loose fitting ring cannot support reaction in the Y direction, right? So it can move. So this is BZ, and it is said that under the action of 2 kilonewton load, right? So here there is a 2 kilonewton force applied at this point, and let's say that this point, the point of application of this force is, let's say, D, right? And it is said that rotation about a line AB is prevented by the cable CD, right? So here we have a cable CD, so this CD prevents the rotation of this frame about line AB. So if I draw that line AB, so this is that line. Let me draw it first. So this is that line AB from A to B. So in this problem, it is given that the whole tubular frame cannot be rotated about this AB line. So this means that the summation of moment about AB line, so this will be equal to 0, right? So this is the equilibrium condition that we have to apply to find the unknowns, right? And it is said that and the frame is stable in the position shown, right? So the frame is stable, so this means that the frame is in static equilibrium, right? And it is said that neglect the weight of the frame compared with the applied load and determine the tension T in the cable, right? So we have to find the tension T in this cable in order to have this condition, in order to have the moment about line AB equals to 0. And it is said that find the reaction at the ring and the reaction components at A, right? So we have to find all the reactions at point A and B. So this will be, let me draw it here, so then this will be the tension direction in this cable, right? So let's say that this is the tension, right? So to solve this problem, we have to apply this. We have to find the moment of all the forces about AB line, right? So as we can see that these AX, AY and AZ, they are intersecting or passing through this point A, and this bx and this bz, they are also passing through this AB line, or they are passing through this B point, and this B point is the part of this AB line, right? So this means that these reactions AX, AY and AZ and BX and BZ, the moment of these reaction about this AB line will be 0, since all of these reactions are intersecting this line AB, right? So we only have to deal with this force. Let's say that this is force, right? So if I mention this is force, right? So we only have to find the moment of this force and this tension in this cable about this line AB. So for that we have to find the coordinates of these points, right? A, B, C, D, and let's say that this is E, right? So there is already a point here, right? So this is D, so this is E. So we have to write the coordinates of all these points. Let's say that this point A is the origin, right? So this is the origin, so the coordinates are 0, 0, 0. Now what are the coordinates of point B? So as we can see that this point B is along Y, right? So the Y coordinate will be 0. Sorry, the X coordinate will be 0, right? So we have to write. So if we want to reach this point B, so then we have to travel along Y. So how much? So this distance from this point to this point, this is 4.5 meters, right? So along Y we have to travel 4.5 meters, and along Z we have to travel this much distance, and this much distance is the height of this tabular frame, right? So this is 6 meters. So along Z we have to travel 6 meters. So these are the coordinates of point B. And what are the coordinates of point C? So this is point C. So this is the along the X direction, and this is in the negative X direction. So you will write -3. So we have to travel -3 meters in the negative X direction, or 3 meters in the negative X direction, right? And since this point C is along the X axis, so the Y coordinate will be 0. Right, and as we can see that this point C is at a height of 6 meters, right? So along Z we have to travel 6 meters from origin. So these are the coordinates of point C. And now what are the coordinates of this point D, right? So if we write the coordinates of D, so to reach this point D we have to travel this 1 meters along X in the negative direction, so I will write -1, and along Y we have to travel 2.5 meters. And since this point D is in the XY plane, so there is no need to travel along Z, so we will write 0. And similarly, if I write the coordinates of point E, so to reach this point E, we have to travel this 2.5 meters in along X, so I will write 2.5 along, since this point E is along X, and there is no need to travel along Y, so this is 0, and we have to travel 6 meters along Z, right? So this is 6 meters. So these are the coordinates, right? So let me write all these coordinates here, right? So if I write, so this is the A, so A is origin, right? The coordinates of B, so 0, 4.5, 6, coordinates of C, -3, 0 and 6, and coordinates of D, so -1, 2.5, 0, and coordinates of E. So coordinates of E are 2.5, 0 and 6. So now if we want to find the moment of this tension in this cable about this point A, right? So if I write the equation for that, so the moment at point A due to the tension T, right? So let me write it like this. So if we use the cross product method, so then this will be R cross T vector, right? So first we have to identify the moment arm for ourselves. So we know from chapter number 2 that moment arm could be any vector from the point of rotation to any point on the line of action of the force, right? So this force. So for that we can define a moment arm for this T. We can define a moment arm from A to D, right? So if I define that moment arm, let's say that this is our moment arm. So this is RAD, right? So if we take the cross product of RAD with T, So we will find the moment at A due to the tension in the cable, right? So this is not the moment at along AB, right? So then we know from chapter number 2 that if you want to find the moment AB, the moment along AB due to this tension T, so what we will do, we will find the moment at point A due to this tension, and we will take the dot product of this moment with the unit vector along that line. So which line? So this AB line. So we want to find the moment of this tension T along AB line. So what we will do, we will take the dot product. So the dot product with the AB unit vector, right? So if we put this in this equation, right, so then this will be RAD cross T and dot the unit vector AB. So we have already learned this, right? So this will give us the moment of tension T along line AB, right? So we need to find this. And similarly, we have to find the moment of this force, right? So if I write, so this will be the moment at point A due to that force F, right? So for that we also need to define the moment arm vector, and this will be force F, right? So we need to define the moment arm for this force, right? So if I define the moment arm, so let's say that this is our moment arm for that force vector, right? So this is RAE, right? So I will write RAE. So RAE cross F. So this will give us the moment of the force about point A. And if you want to find the moment of this force along line AB, about AB line, right? So we will write MAB of this force, and this will be RAE cross F, and we will take the dot product with AB. And remember that this is not the vector, this will always give us magnitude, right? So this will always, we have discussed this is scalar triple product. So scalar triple product, so this always gives us scalar quantity, right? So this always gives us magnitude. So this will give us the magnitudes, right? So when we find both of these and we take the summation of both of these, if I write, so the summation of moment about AB equals to 0. If we apply this equation, so then this will be equal to, I will write that MAB due to tension T plus MAB due to that force F will be equal to 0, right? And the remaining reactions are not producing moment about this AB line, right? So they are already 0. So now we have to deal only with these two equations, right? So now in these equations, we can see that we need to find this vector, we need to find this T vector, and we need to find this AB unit vector. Similarly, we need to find this RAE vector, this force vector, and this unit vector. So first I will find the RAD vector, right? So if you want to find RAD, so now I can remove this, right? So let me remove this. I will put this aside, right? So I will place it. This is our main condition, right? So I will put it here. Let's see. I will find this moment arm, right? So this is our RAD, right? So I will write RAD. So this RAD is the moment arm for this tension in the cable, right? So RAD. So we know we have the coordinates of point D and the coordinates of A. So we can write this RAD vector directly in terms of these coordinates. So this will be minus I plus 2.5 J and plus 0 K, right? So this is that RAD vector. Similarly, we can find this RAE vector, moment arm, right? So RAE is the moment arm for this force vector, right? So RAE. So this is RA and these are the coordinates of E. So we can directly represent in the coordinates of E, right? So this will be 2.5 I plus 0 j plus 6 k, right? So when we want to find a vector, so we will subtract the coordinates of A from E, right? So if we subtract the coordinates of A from E, so we get this, right? So and then we have to write the force vector as well. So the force vector, if I write the force vector, so the force, this 2 kilonewton force is acting along Y. So we will write 2 and this is acting along positive J, right? So this is the vector of that force plus 2J, right? And now we have to find the T vector. So T vector will be equal to T magnitude, which is unknown, which is required. We need to find this T, and this will be this T tension in cable is along CD line, right? So we have to find the unit vector along CD. So this T, so we will find CD vector divided by CD magnitude. So this will give us T vector. So now I will write T and CD. So this is point C, right? And this is point D. So we have to subtract the coordinates of C from D, right? So I will write minus 1 minus 3, right? So this will become plus 2, 3, sorry. So this is minus 1 and minus 3, right? So this is along I, and 2.5 minus 0. So this will be plus 2.5 J, and this is 0 minus 6, right? So this will be minus 6 K, right? So this is plus 2I, right? So I will write plus 2I, and we will divide this by its magnitude as well, right? So this will be 2 square plus 2.5 square, and this will be minus 6 square or plus 6 square, doesn't matter, right? So we will take the square root. So this will give us the T vector. So if I write that T vector, so T vector so this magnitude comes out to, this is 46.2 under the root 2, right? And we will multiply this with 2I plus 2.5 J minus 6 K, right? So this is the T vector. And we have to find the unit vector along AB, right? Since we want to find the moments along line AB, so we want to find this unit vector. So this will be AB vector divided by AB magnitude, right? So these are the coordinates of point B, so we can write. So this will be NAB. This problem is not difficult. You people have to find the way. You people have to learn the method, right? So it's very simple, but once you people know this condition, that what is meant by this condition, so then it's very easy. Only we have to deal with the coordinates of the points, and we have to find those vectors, right? So this is NAB vector. So this will be AB vector divided by AB magnitude. Since A is the origin, so we can represent that AB vector in terms of these coordinates. So this will be 4.5 J plus 6 K and divided by its magnitude. So it is 4.5 square plus 6 square, and this is under the root, right? So when we solve this, so this magnitude comes out to be 7.5, right? So this is 1 divided by 7.5 into this, right? And you people will observe that in books they have written this in some other form, right? So if we multiply this with multiply and divide this with 1 by 5, right? So this will be, let's say that this is 1 by 5 and 5 divided by 7.5 into 4.5 J plus 6 K. And now if we multiply this fraction inside, right? So we will get that same unit vector in like that book, right? So in the book example they have written this NAB in this form, right? So this is 1.5 and they have multiplied this with this. So if I so when we multiply this fraction inside, so then we will get this unit vector along AB, right? So you people will find this unit vector in the book solved example, right? So this is that NAB vector. It doesn't matter, we can solve this problem by using this as well, right? So but they have written it like this, so I have told you people that this is the way that how they wrote that NAB unit vector. So now we will apply this equation again, right? So now we know all vectors, right? So again, if I write, so the summation of moment about AB equals to 0 is equal to MAB of T, right? So we will write RAD cross T vector and the dot product of NAB unit vector plus, and the moment arm of this force is RAE, right? So again we will write RAE cross force vector and the dot product of NAB, right? Since these are the scalar triple product, so we can write it like this. So we will write RAD. So where is RAD? So this is RAD, right? So this is minus I plus 2.5, right? So we will write minus 1, 2.5 and 0, right? And then the T, so this is the T vector, right? So we will take this common, right? So this will be T divided by 46.2 and this is 2, 2.5 and minus 6, and this AB unit vector, so this is 1 by 5, right? So I will take common 1 by 5 as well, so 1 divided by 5, and this is 3j plus 4k and this is 0, right? And we will write plus RAE, so this is RAE, right? So we will write 2.5, 0 and 6, and the force vector is this is 2j, 0 and 0, and NAB, again this NAB is that same vector, right? So we will write 0, 3, 4 and this 1 divided by 5, so we will write it like this. So this will be equal to 0. So if we take 1 by 5 common from this and multiply both sides or divided by both sides, so since we have 0, so this will be cancelled out, right? So throughout, so we will be left with only these things. So now we can find this, so this will be, and this is 46.2 under the root 2, right? Remember, right? So this is T divided by 46.2, right? And this, if we take the determinant of this, so we need to hide this and this, right? So we will write minus 1 and 2.5 into 4, or I can write that this will be 2.5 into 4 minus, and this will be minus 18, right? So this will become plus, and now we will hide this column and we will take determinant of this, and this is 2.5. So with 2.5 we will write minus, this is determinant method, minus 2.5, and 2 multiplied by 4 is 8, right? So this is 2 multiplied by 4, so it is 8, and this is minus 0, right? And if we hide this column, so this is 0, so everything will become 0, right? So this is it, and now we will write plus, and now we will take determinant of this, so we will hide this and this, so 2.5, and this will 2 4s are 8, right? So this is 8, and this is 0, so minus 0. And now if we hide this and this, right? So this is 0, so everything will become 0. And now if we hide this and if we take the determinant, so 6, 0 into 0, 0 and 0, 0, so everything becomes 0, right? So this is it, so this is equal to 0. So when we solve this, so we get this, right? So this is like this. So now we can find T, right? So T, this will be minus 48 T divided by this 46.2, and this will be minus 20. So T comes out to be 2.83 kilonewton. So this was required, right? So if there is this much tension in this cable, right? So we will have the moment about this AB line equals to 0, right? So this is the tension which was required, 2.83 kilonewton. Now we need to find the reactions at point A and B. So now we know this T, right? So if I write, now let me remove these, right? So now the T vector will be equal to, so now we know the T magnitude, right? So this is 2.83 divided by 46.2 under the root 2. This will be 2I plus 2.5 J minus 6K, right? So now we know all the components of T vector as well, right? So if we find this and if we multiply this, so we know the components of this T vector. So let me find. So now this is our T vector, right? So now we know the components of this T vector, right? So this is this is Tx component, this is Ty, and this is Tz, right? So now if we want to find the reactions at B, right, so we have to apply some other conditions. So let's say that the summation of moment along Z equals to 0. If we want to apply this condition, right, since the system is in equilibrium and this is the Z axis, remember, right? So for that we have to look into the forces in this direction, right? So we will find the moment about Z by using the inspection method, right? So now as we can see, if this is the Z axis, right, so these AX, AY and AZ, they are passing through that Z axis, or they are parallel to that Z axis. So they will never produce the moment about Z axis, right? So these AX, AY and AZ, they are eliminated, right? So this BZ is parallel to the Z axis as well, so it is not producing any moment. So only this BX is producing the moment about the Z axis, and the direction of the moment produced by this BX will be like this. And if we curl our right hand fingers in this direction, so the thumb will point out in the positive Z direction, right? So if I write this equation, so this will be BX, and the perpendicular distance of this BX, again we are observing the forces from Z direction. The BX force is along X, so the perpendicular distance will be along Y, right? So remember, so the perpendicular distance of this BX along Y from the Z axis is this 4.5, right? So we can write that this is 4.5x, right? Let me write it with some other color. So this is 4.5 bx, right? And similarly this force F. So again we are looking into this force from the Z direction, right? So Z direction, and the force is along Y, right? So this force is along Y. So the perpendicular distance will be along X from the Z axis. So this is the perpendicular distance of this force from the Z axis, right? So we will write, and this 2 kilonewton force will produce a moment in this direction about the Z axis. And again if we curl our right hand finger, so the thumb will point out in the positive Z direction, right? So I will write plus, and this will be 2 kilonewton times this 2.5, right? So I will write 2.5 into 2, and this will be equal to 0. Okay, there is one another component as well, right? So if we draw the components of this tension as well, right? Let me draw the components of this tension in the cable as well. So this will have one component along X, and we know that that component is along positive X, right? So this T will have one component in this direction. This is Tx, remember, right? So this is Tx, and there will be another component is in the positive Y, right? So first let me draw it here first, and I will move it, right? So this is Ty, and this is Ty, remember, and there will be Tz, and Tz is in the negative Z direction, right? So we can say it from here. Okay, so I will draw it like this, exactly vertically downward, right? So this is Tz. So now we are finding the moment about along Z axis, right? So this Tx is passing through the Z axis, it is intersecting, so it will not produce any moment about Z. This Tz is parallel to the Z axis, so only this Ty is producing the moment about Z, right? So we will consider that Ty in this equation. So Ty is 1.04, so I will write 1.04, and this Ty will produce the moment about Z axis in this direction, this direction, right? And if we curl our right hand finger, so the thumb will point out in the negative z direction. So I will write minus, and this ty is along y. We are observing the forces from z, so the perpendicular distance will be along x, right? So the perpendicular distance of this ty from along x is this 3 meters, right? So I will multiply this with 3, and this will be equal to 0. So now we have this equation, and there is one unknown, so this means that we can find bx by using this equation. So let me find that bx. So when I solve this equation, so bx comes out to be minus 0.417 kilonewton. So this means that the original direction of bx is in the positive x direction, right? So we have to reverse this direction. So this is the magnitude of bx. Now if we take the summation of moment along x equal to 0, and this is our x-axis, right? This is our positive x-axis. So we need to observe the forces in this direction, right? So as we can see that again these ax, ay and az, they are passing through that point A, and they are intersecting this x-axis, so they will never produce the moment about the x-axis, right? So they are eliminated again, and in these two components, right, this bx, this is parallel to the x component, so it will not produce the moment about x. Now this bz will produce the moment about z, right? So this will be included in this equation, so we will be able to find this bz, right? So let me write it here. So this will be summation of moment along x equal to 0. So we will write bz. Again we are observing, inspecting the forces along x direction, right? So x, this bz is along z, so the perpendicular distance will be from along y, right? So the perpendicular distance of this bz from the x-axis will be along y, right? So this distance, this is 4.5, right? So we will write 4.5 bz, and this bz is producing the moment like this. And if we curl our right hand fingers in this direction, so the thumb will in the positive, will point out in the positive x, right? So this means that this moment is positive. This means that this moment is counterclockwise from this direction, right? And now if we observe the components of this tension T in this cable, right? So this Tx is parallel to the x-axis, so it will not produce any moment. This Ty, so I will write Ty. So Ty magnitude is 1.04, right? So I will write 1.04, and we are observing the forces along x. The force is acting along y. So the perpendicular distance will be along z, right? So the perpendicular distance of this Ty from the x-axis along z is 6 meters, right? So I will multiply this with 6, and let's say that this is my x-axis, right? So this Ty will try to rotate the system like this about the x-axis, right? So if we curl our right hand finger, so the thumb will point out in the negative direction, right? So I will write minus. This Tz is not producing the moment about z, right? Why? Because this Tz is intersecting the x-axis. If I extend this Tz until this point, right? If I extend this like this, so this will intersect the x-axis. So this Tz is not producing the moment about the x-axis, so only this Ty is producing the moment about the x-axis, right? And this force is also producing the moment about the x-axis, right? So we will write 2 kilonewton. This force is along y, right, observing along x, so the perpendicular distance will be along z, right? And the perpendicular distance of this 2 kilonewton force from the x-axis is 6 meters, right, along z. So I will multiply this with 6, and this force will produce the moment about the x-axis in this direction like this, right? So if we curl our right hand fingers in this direction, so the thumb will act in the, will point out in the negative x direction. So I will put minus sign here, and this will be equal to 0. So now if we solve this, so we will get bz. So when we solve this, so bz comes out to be 4.05 kilonewtons. So these are the two reactions at point B. So now we can apply the summation of forces along x equal to 0, right? So we will add all those forces which are acting along x, right? So this ax is in the negative x direction, so I will write minus ax, right? This bx is in the negative x, so I will write minus, and we know the magnitude of bx, right? So this is minus, so minus into minus will become plus, and this will be 0.417. this is bx, right? Minus bx, and this tx is in the positive x, right? So we will write plus, and the magnitude of tx is this 0.832, so I will write 0.832, and this will be equal to 0. So this will give us ax. Now if we apply the summation of forces along y equal to 0, so the summation of forces along y equal to 0, so this ay is in the negative y direction, so I will write minus ay, right? There is no component of b along y, and this force, this 2 kilonewton force is along positive y, right? So we will write plus 2, and this ty is in the positive y, so the magnitude of that ty is 1.04, so plus 1.04, so this will give us ay. And if we apply the summation of forces along z axis is equal to 0, so this az is in the positive z direction, so I will write plus az plus bz, and we know the magnitude of bz, so this is 4.05, so I will write plus 4.05, and tz is in the negative direction, so I will write minus, and this is tz, right? So this is 2.496. so when we solve these three equations, so we have three equations, three unknowns, so we will find the reactions at point A along x, y and z. So let me solve it. So when we solve these three equations, so ax comes out to be 1.25 kilonewton, ay comes out to be 3.05 kilonewton, and az comes out to be minus 1.55 kilonewton. So this means that we have to reverse the direction of az, right? So the actual az, the actual reaction along z is acting in the negative z direction, right? So we have to reverse this direction. And we can find the total reactions at point A and B, right? So if you want to find the total reaction, the resultant magnitude at point B, so this will be bx square plus bz square, right? So you people can find it, and similarly we can find the magnitude, the resultant reaction at A, so this will be ax square plus ay square plus az square under the root 2, right? So you people can find it yourself. So I hope you people would have understood this simple problem, this very important concept, right? So you people need to practice it, and from my side this is the solution of this simple problem, right? So kindly like my videos if you people like it, and share it with your friends as well.